Hello everyone, myself Deepak Kohli from JNT College, PSC Regular. The professor is G. Raju. I am going to present my topic today, which is analysis of series and parallel RLC circuit. Let's start this topic by introduction, where the RLC circuit consists of mainly components of RLC. There are implies resistor, inductor, and capacitor. We know that when these all components connected in series, then we call it as RLC circuit. Otherwise, if they connected in parallel, then we call it as parallel RLC circuit. Today, I am going to divide this topic into five subdivisions. Where I am going to talk first one RLC components, next phasor diagrams, next series RLC circuit, next parallel RLC circuit, and finally resonant condition. However, I am going to talk summary at last. Let's start our first subdivision RLC components, where uh, resistor. We know resistor opposes the current flow. We know that inductor stores the energy in magnetic field. Capacitor stores energy in electric field. These all are indicated as resistor as indicated as R, inductor as L, capacitor as C. The inductive reactance is 2 pi FL. We also where capacitor reactance is 1 by 2 pi FL, or else we can call it as 2 pi FL as omega L and 1 by omega C as capacitor reactance. This phasor diagrams of these these components. When the resistor is singly connected in the circuit, we we call it as purely resistive circuit, where we can see the phasor diagram. The phase difference between V and I is zero. They are in phase. This is the purely resistive circuit phasor diagram. Where we see in capacitive circuit, the angle between the capacitive voltage and capacitive current is 90 degrees, where current leads the voltage by 90 degrees. In inductive circuit, uh, here also the inductive voltage and inductive current is are in 90 degrees, but here voltage leads the current. This is the difference in capacitive circuit, purely capacitive circuit and purely inductive circuits. Here, this purely capacitive circuit and purely inductive circuit are not in phase, but the purely resistive circuit will be in phase. Let's move to the topic series RLC circuit. Here we are going to talk about impedance, where impedance is known as a combination of R capacitive reactance and inductive reactance. It is known as impedance. Impedance, if we talk impedance for single components, like for R, the impedance will be R. For L, the impedance will be I into 2 pi FL or I into omega L. Impedance of capacitor will be 1 by I into 2 pi FL, or we can call it as 1 by I into omega L. These all are for only single components. When only the circuit consists of R, or only the circuit consists of inductor, only the circuit consists of capacitor. If we talk about the uh, uh, full circuit, which consists of RLC, the total impedance in this RLC circuit, where this RLC are connected in series, the total impedance will be we will indicate this impedance as Z. Z equals to R plus I into 2 pi FL minus 1 by 2 pi FL, or we can also indicate it as R plus I into 2 pi omega L minus 1 by omega C. Here we can see the series RLC circuit diagram, where the current will be same for all these resistor, capacitor, and inductor, but the voltage will be divided for resistor, capacitor, and inductor. Uh, Here the voltage is equals to this is a AC circuit, so voltage is equals to V sin omega t, and I is equals to I sin omega t plus phi, where phi indicates the angle between voltage and current. Here plus then we'll get plus when current leads the voltage, and we get minus when current voltage leads the current. These are two conditions when we get minus pi or plus pi. We will see in later. Further, we move. The in series RLC circuit, we will contain three cases. The first case we'll talk about inductive voltage is greater than capacitive voltage. In this case, we can see in the diagram that capacitive voltage, inductive voltage are started from same point. The source voltage will be, sorry, uh, here inductive voltage is greater than capacitive voltage, so we will indicate y-axis as VL minus VC. If capacitive voltage is greater than inductive voltage, we will indicate y-axis as VC minus VL. So first case is VL is greater than VC, so we'll talk about VL minus VC. Here the resultant voltage will be square root of VR square plus VL minus VC whole square. We know that by seeing the diagram. For further calculation, we get finally Vm is equals to I into root of squares R square plus XL minus XC whole square, where XL and XC are the reactance of inductor and capacitor. Finally, Vm can be denoted as Iz, where Z is equals to impedance, which represents R square plus XL minus XC whole square. If we move to the second case, here in second case, we'll have VL is less than VC. In this case, the y-axis will contain VC minus VL because VC is greater than VL. So the resultant voltage in this case, we get root of VR square plus VC minus VL square, since VC is greater than VL. Further calculation, we get Vm is equals to, by commoning an I and removing outside, we will get I into root R square plus XC minus XL whole square. Finally, the this finally the source voltage is equals to Iz, where Z is the impedance. But here is the impedance will be root of R square plus XC minus XL whole square. This is the two cases with, where will we overcome in series RLC circuit. If you move to the parallel RLC circuit, in this case also we will contain three cases where but here in parallel RLC circuit, if you see the circuit diagram, all the components will be in parallel. So this is called as RLC circuit. But here current will be not same for all components because they are in parallel. But here voltage across all the components will be same. So we'll see the phasor diagram with respect to voltage. Uh, Here the current is not same for all components, so we will indicate this current in y-axis. In first case, if we see the inductive current is greater than capacitive current, so in y-axis we get IL minus IC, since IL is greater than IC. The resultant current will be get by solving this equation. We'll get this. If we see in second case, the inductive current is less than capacitive current. So in y-axis, we get IC minus IL, where IC is greater than IL. By solving, uh, we get the by solving we get the resultant current. Here, in both this parallel and series RLC circuit, the third case is resonant condition, where in series RLC circuit, VL is equals to VC. In parallel RLC circuit, IL is equals to IC. This indicates XL is equals to XC, where omega L is equals to 1 by omega C. Finally, we get the frequency, where frequency is equals to 1 by 2 pi under root LC. This is the resonant frequency. Resonant frequency will get when circuit is in resonance. In series, we see that resonance current will be maximum and impedance will be minimum. In parallel, we see current will be minimum and admittance will be maximum. Where here we in series we call it as impedance, in parallel we call it as admittance. Both are same only. But if we see the condition, both will be opposite. Here current will be maximum, and here current will be minimum, and impedance will be minimum in series, and admittance will be maximum in parallel. Let's move to the topic applications of RLC circuit. RLC circuits are used worldwide. If we see some of the applications, the RLC circuits are used in tuning circuits, where tuning circuits indicates radio receivers and transmitters, and also TV receivers. Uh, RLC circuits are also used in filters. The filters means low pass filters, high pass filters. There are different filters: band pass filters, band stop filters. These are the four filters where RLC circuits are used. Impedance matching or impedance matching. In here also RLC circuit is also used. Impedance matching means communication system. Final application is resonant power transfer, wireless power transfer. This means wireless power transfer. These are the some applications where RLC circuit is used. It, it means if we move to the summary, what I have finally, if we see the summary, what I have talked in this topic, in series RLC circuit, I have discussed about the resistor, inductor, capacitor, and impedances. Where impedances, this is the formula I have discussed in the first only. With resonance, I have discussed also resonant condition in RLC circuit. Current, I have discussed about current and applications. These are all the summary which I have discussed in previous. If you see in parallel RLC circuit, I have discussed about the RLC resonance condition, current through the components, and voltages also. I have also discussed applications of parallel RLC circuit. Uh, this is the topic of analysis of RLC circuit which have been discussed today. Thank you.